Hello and welcome to the Extended Greg YouTube channel. I'm Greg and today we're going to be building a reader for Quadrature Encoding. Quadrature Encoding is great because we can track the actual position of moving objects, and it's going to be a very exciting time. We're going to be using the Raspberry Pi Pico as well as just kind of prepping ourselves to be able to apply this as like a home-built servo in our own projects. Before we get into it, be sure to hit that like and subscribe button, but let's get right into it. Okay, so this is going to be the motor that we're actually using in order to be able to do this. This one happens to be a gear motor. And what it is it has a quadrature encoder on the end of it. And pretty much what it is it's two sensors at 90 degrees to each other, and then a magnet attached to the actual input shaft, or at least the armature of the motor, to be able to provide feedback for where it is, how many rotations, how many pulses, for example, which tells you what direction, okay? Because it's important to know whether you're going forward or backwards, but then also how far, because we're going to know based on how many rotations that the input shaft does, because it's hard attached to the actual output shaft through some gearing in this particular case. It will tell us how many rotations we've done there, or how much of a rotation. So what quadrature is pretty much it's two, because the sensors are offset by 90 degrees, and we have a magnet that has north, south, so it's going to be 4 pulses per. It's going to pretty much be 2 signal trains that are slightly offset from each other. And based on which pulse, like let's call this A and let's call this B, right? So A would be this one right here, and B would be this one right here. So as it passes, it will go high when the magnet is close to it, right? So as this magnet spins, it will bring A high, and then, I'll point using here actually, it'll bring A high, and then it will go down as the magnet passes, right? B, since it's offset, will go high, and then will go low as well. So you could tell that because A is going high before B, that it is rotating clockwise in this particular case. If it was the other direction, right? So you had A, that would go high, whoops. So if you had A going high after B, we would know that it would be going in the counterclockwise direction. So that's pretty much what we're going to be reading. So I've actually already done a little bit of investigation just to make sure, so you know, we can make sure things keep moving. But we're using Google Gemini to be able to help write this code, just because it's going to help expedite things significantly if we have the computer do the work. That being said, we're probably going to be debugging it and tweaking it a little bit to be able to get things going, but I think that's just fine. So we're also going to be using Thonny for this as well. So the first thing that we're going to do, we're not going to go through the code just yet. We'll load Thonny and then we'll actually get in all of this code into it. So it comes with some good explanation, things like that. I'll just kind of walk through exactly what it has here, and hopefully Thonny loads at some point. But we're going to import a number of packages, and then we're going to define our pins. And pretty much what I've asked it to do is to give us a count and a direction. So a speed and direction. So counts per second, etc. And then it's going to define a function for a quadrature decoder. There it is. It's going to define a whether it's going, you know, it's going to decode what we just discussed. And then pretty much from there, it's going to create a state machine to be able to track that. I'm not going to go into what that is, but I think that's an interesting use and very appropriate for it. So it's going to get the position by actually converting it based on the counter value, pretty much just incrementing or decrementing it based on the actual direction to be able to get that position. And then it's going to get the speed based on that actual change over time. And then just at the bottom, it's going to give us the position, it's going to give us the speed. Just so you know, the speed itself is actually based on, it gives us an explanation of what it is here. It divides it by 4 because of the quadrature itself, but technically there's 4 poles, so there'll be 4 other state changes as this actually rotates. As this actually rotates, just because it's going to be, you know, a little off the ideal. It's not going to be 1 pulse train per rotation. So we'll have to play around with that and just make sure. So we're not going to be doing an actual motor controller for this particular thing. So we're not going to be fleshing this out just because I think it's going to take a little bit too long to be able to do that. But we will, in future videos, be actually integrating this so we can do joystick control and things like that, kind of like what we did with the pan tilt project, or at least got started, and see if we can finish that up. So we've copied this into the clipboard. We're going to go in here. We have a new file. We will paste that right in. So let's actually connect up our Pi Pico. Right, and I have a brand new one that I just took out of the package. I took a picture of it for the screenshot, so that's the only reason the plastic is off of it. But what we're gonna do is just plug it in for the first time and then get Thonny set up so that way it actually runs Micropython. So you notice it opened up with a folder. It actually will mount itself if it doesn't have any code to run or anything else like that. It will open up as a external drive, and that's usually how you would load on programs, things like that. In this particular case, we are going to run Micropython, so I'll get myself out of the way here really quick. So we're going to click in the bottom right here. It will open eventually, assuming it doesn't want to freak out, and wait. And still wait, and wait a little bit more. Maybe even a little bit more. There it is. So we're going to install Micropython. Okay, we have the option of Micropython or CircuitPython. Raspberry Pi Pico does support both, but we're going to be using Micropython for this just because I think it's a little bit better documented and everything else like that. So we're going to be choosing the external drive that showed up, which in this case, there's only one of them. We're going to be choosing our family, which is the Raspberry Pi 2. And I mean, that's really the only option in terms of Raspberry Pi. Wait. Thonny is going to do a Thonny thing and potentially crash. We're going to choose our variant. We're going to choose the WH just because that's what this happens to be. And then we're going to choose our version, which we're going to use the latest stable. There's no reason not to. And we're going to do install. There's no blinking lights or anything else like that that we can look at. So we're just going to wait for this to finish. And then we'll have we're going to have Micropython installed on a Raspberry Pi Pico. Excellent. And look, it looks exactly the same. So, wonderful. Now, here's the key thing. So, we're actually going to be seeing the interpreter down here running on the actual COM port for the Pi. So, when we run things in the interpreter and in the shell at the bottom of Thonny, it will actually run on the Pi itself, opposed to just a general interpreter. And hopefully, it's not going to be a massive pain. So let's see. Right, so COM5 is the appropriate one. We do see that it is the Raspberry Pi Pico, so everything's good there. So I'm going to hit stop reset, and that brings us to the command prompt on the Pi. So we're going to run this out of the box, okay? Right now, we don't have anything connected to it. We do need to define our pins. So we need to decide what we're going to hook up, how we're going to hook this up. And we also potentially want to actually verify that what our wiring is for our motor. So first things first. Let's find out what our motor connections are, and let's just solder them up so we have something here. I'll move the Pico out of the way for the moment. So to do this, I'm just going to use a multimeter. Technically, I could just look it up, but there's a pretty easy way to do this. So right here, I have a multimeter. It was already on audio. So when we touch the two probes together, it makes a beep. So I do know that these outer two wires right here, the red and the white, don't ask me why it's red and white, those are actually the power pins for the motor itself. And they go to those, here I have pointers. It goes to these two pins right here, which are actually just the motor leads. There's nothing special about this motor except that it has a magnet and some sensors on the back. So, you know, nothing going on internally. And it should be these two go to this sensor, and these two go to this sensor. We're going to find out if polarity matters right now. Right? And I'm going to use a third hand, try and rotate this around. We see we get nothing, so we're going to reverse those two connections and see if we get something here. All right, maybe that's not it. Let's see. So I'm going to do this one right here. Let's go through them one at a time. And this is just a little IC, so it does actually, it's a transistor-based switching mechanism, so it does care which polarity is which. I'm going to set this to diode setting as well, just to make sure that we're getting enough voltage to actually read, because that could also be part of it, is we're not actually inputting enough to be able to overcome it. And that's not really doing anything, which is fine. Let's just try swapping it really quick and just make sure. Okay, so black is negative, yellow is positive, as we would hope. I am just going to check. We should not have any continuity going to the other connection, because these should be independent, but we do. Oh, that's wonderful. I may need to look up the data sheet. Because there's not supposed to be really any other additional logic on this. But sometimes they do their own thing. Well, let's see what we got. This is not one of those things where I've gone through it before with this particular motor or anything else like that. This is kind of a project that I wanted to do for myself. So this is me doing it in real time. All right, let's see what we got. Now, we could trace this out the other way, too. Alright, so it's going to make a beep. Slightly out of focus, but you know what? I think we can live. Oh, a little bit better. So we're gonna just tone these out individually, right? So we know that this one goes to here, because we can see the giant trace. Helps if I touch it, right? And then we see another one that goes underneath the magnet over to this sensor right here. And it looks like there is a diode on here, which is very nice. So this blue wire should run over here, right, through this resistor. So if we touch right here, on this resistor, we should get a tone. Right? And we do. On this diode right here, let's see where this runs. Green wire. So where's the green wire go? No idea where the green wire goes. Alright, that's fine. Yellow wire should run to the other resistor right here, similarly. Or... okay, nothing there. Nothing there. I don't think there's any electronics underneath. But theoretically there could be. And it doesn't look like it. Alright. Well, it's enough messing around. Let me actually find the data sheet. This is a one of those cheap parts, so it doesn't have an actual data sheet, it just has a posting for whatever they happen to put on Amazon. Let's see. Whoop. Let me find out what this actually is. All right, and let's do... You're not going to be able to see this. All right, so here's what it says. Red is motor power plus. Black is the coding power negative. Yellow is feedback, green is feedback, and blue is coding power positive. All right, so let's write that down. So it does have a positive and negative rail. Where's a pen? So we have red, so motor power plus, black is coding. It says coding, but it means the Quadrature encoding. So it's going to be signal power negative. Then we have yellow, which is going to be let's see, it does have a title on it. I don't know if you can read that. It's even small for me, but it's we're gonna call that A. Then we have green, which we're going to call B. And then we have blue, which is going to be our signal power positive. And then, of course, we have white, which is going to be our motor power negative. So that's our actual output right there, or that's our current pinout right there for this motor. So, and it is, I'm just gonna write this down as well, but it's 3.3 to 5 volts, and our motor power is 12 volts. So I don't know if is that just as blurry as it was before? Bear with me. So that's what we got. Okay, wonderful. So back up here, we need to determine our actual pins that we're going to use for this. So let's just look up the Raspberry Pi pinout really quick. I mean, technically, actually, we could just look at it. Because nice thing about this is there's actually they're just contact closures or just voltages that we're going to read. So they're just straight digital inputs. We don't need any kind of special pulse width modulation or anything else like that involved. So we can use any of our standard GPIO pins, which there are plenty on the Pico. And we're going to provide it also 3.3 volts to the signal side, as well as a ground connection. And we'll solder those up here in a second. We're not going to connect to any of the motor side. We're going to be driving that with an external power supply. But I think that, you know, it's going to be more than fine for being able to read this. So let's arbitrarily choose 3 and 4 as our actual sensor inputs. So we'll put write that down there. Okay, so I'm just gonna solder these directly, for better or worse. So first thing I'm gonna do is just unplug it. I'm not gonna do that while it's live. And we're gonna find out if this all works. Now, just to kind of dress this up as well, I'm just gonna twist some of these leads together to be able to see these matched pairs a little more easily. Oh, and Fizzies, how are you? I see you said hello in chat. Thanks for joining. So then blue and black are going to be our power connections. So we'll have our ground and our 3.3 volt. And there's no real reason to need to do this. I just like it better when the cables are a little bit dressed and neat. And then the two quadrature outputs are the green and yellow. And then I'm gonna twist all of the signals together. So the only thing we have are two braids. One's coming out, that's for motor power, and the other one is coming out is just for signals. All right, the soldering iron should be warmed up by now. And I'm just gonna freehand this, which is gonna go great. So referring back to our pinout, we need 3.3 volts for our blue wire and ground for our black wire. So up here we have 3.3 volts for the blue. And actually I might just do this on the castellations. Let me get a soldering iron. Otherwise, this is going to be impossible to try and hold and do at the same time. All right, that should be enough hands. So, right, we have our ground, which will be this right up here. So pin 3. And I could strip off more of this. I am going to disconnect it from the motor just so we're not fighting the weight of that trying to flop around. So pin 3 here. And just as a little trick, the square pins are all ground. All right, and we'll just touch it with a little bit of solder. And that should at least hold us on so we can get the blue wire, which is going to be 3.3. I am going to twist it a bit more, make it neat. See if I can focus it a bit better for you. All right, and then we'll twist this around. And then we decided yellow was going to be 3. And green was going to be 4. So let's go ahead and do that. Now, normally I would do an actual breakout connection on like a PC board or something like that to be able to make it so I could remove the microcontroller, but for the purposes of this example, I think it's just fine. I could always desolder it and put in header pins later. But that's all we need. And I'm going to use an external power supply for these, so I'm going to leave them free floating, and I'm going to refocus the camera. Which, by the way, this camera has the smallest depth of field I've ever seen in my life. So, alright. So now we got this. We're just going to be reading the serial console output, so we don't actually have to care about Wi-Fi or anything else like that today. But it will be something that we'll add in the future. So we will connect this back up to the motor. We'll connect it back up to the computer. And we'll go back over to KVM. All right, let's see what Thonny is unhappy about. The connection was lost. Well, that makes sense. So, we have this right here. Let's just try running it straight out of the box. So we know our pins now. So for A, it's going to be GPIO 3. It says actual pin number. Well, let's try it. Let's see. It would be pins 5 and 6, it looks like. But let's just try GPIO number. Actually, before we save it, let's just run it. Pin A is not defined, so let's try. And this just may be the decoding, so it's not actually pulling it from the global variable that's defined here. So it's giving us this error where it says the line 22 in quad decoder. So quad decoder here. So it's saying on line 22, wait for pin A. So what we may need to do is define a global. And we'll do pin A and pin B. Just so that way it does reference those normally. And let's see. And we may have actually hit an error earlier, but it's not saying it for some reason. So normally, right, because we have machine import pin here. So pin itself, yeah, let's switch this back. And we can go to our explanation as well. So pin define the pins that are connected to the motor's quadrature encoders, etc. That shouldn't be an issue. So let's see why it's not actually doing anything. Still says it's not defined. I mean, it's clearly defined, but let's just double check down here. No, we don't actually need it here, I don't think, because we're doing this. Where is it calling this from? So it's saying 262 in RPi 2py. So line 14. So what's being called on line 14? Do we have this installed? Let's check that. So what we'll do is we'll check and make sure that we actually have that library installed. That's usually one that's a default, but we'll make sure that it is actually installed in Thonny and that it's present and available for it to use. No reason it wouldn't be, because we installed the RP2 variant of Micropython, which is supposed to include it, but let's just double check. It isn't throwing an include error, so I do think it is including, but it's saying it's not defined, so it could just be an issue with our syntax. And I'm not sure why it keeps hanging like this. That is not at all concerning. Actually, there is one way that we can easily try and troubleshoot this, which is we can just give our error back into Gemini and see what it says. Since Thonny is being a little unhappy. And I just copy the full trace back if I'm going to do it this way. So what it's saying is to actually add it as a as an argument. We did try the global keyword. Oh, but we didn't do it outside of the scope. Well, let's try what it said first. Let's do that. So pretty much what we're going to do is we're going to add pin A and pin B. As two variables that will pass into it. We need to find out where this is being called from. Let's try it. Two positional arguments. It looks like it is actually trying to pass it through, but it's not able to pass these variables. So that's one thing. So let's get rid of that. Let's do the global, which was the second suggestion that it tried. Remember that AI is not necessarily the best at it. Oh, actually, no, we didn't complete it. Under our state machine. Wait a minute. So we'll put that back. Let's see. Yeah, I don't think that's gonna do it. I still think the global method is probably going to be the best. It says not recommended. But we can define it. Now it's saying define it in the global scope. So we'll try that. Ah, I see. So it said we redefine the variable as global. Okay, and now let's do global. Oops. So let's see if we can figure out what's going on here, because it's calling a library, which is what this add is. So it's saying the auto push true, So it's pretty much creating what looks like an interrupt, and that's causing it to have issues referencing this particular pin. So I'm not entirely sure why, but let's see. Let's see what we can figure out here. Let's actually ask it. Is it going to give us the whole code? It's going to give us most of it. Alright, so it gave us the first part once again. So let's try copying that in. Did give us everything to here. So let's just replace that. Let's try running it. Name X is not defined. That's fine. Let's replace this. So it's GPIO 3 and 4. And we should actually put in Pico in here as well. And let's just make sure that it is, in fact, referencing the way we want it to. So import R2, Pi 2, I should say. Pin 0, GPI 0. Right, so we are referencing it by GPIO number, which is the appropriate way to do it. I don't believe we need pull in. We're not doing pull in, pin in. We are using PIO though, which is what we're doing here. But here it does say 25. So we could try and define it directly. So set initial, PIO, out low. Slightly different, but that's fine. So we are defining it correctly, at least as it defines. Let me make sure as well. All right, I'm on GPIO 3 and 4. Let's see what's going on. Let's just try running it again. 1 positional argument, 0 were given. Let's just feed that back in, see what it comes up with. I will say this, the advanced Gemini is a little bit better at it than the regular one. I don't have it on this account. Oh, is it defined down here? Wait a minute. Ah. I didn't actually notice it. Okay, so let's do this. I want to do pin A and pin B because we know that those are 2 things that it's going to need from the global scope. Let's try running it. 2 positional arguments. We have the 2 positional arguments there. Great job. Function takes 2 positional arguments. Is this the same word? Yeah. Let's save this. There it goes. Okay. So what it said was not accurate, which was putting in the argument as an object. And it is entirely possible that there's some syntax change that Gemini is not aware of that we would need to account for. So now it's giving us the full code because it's saying this is right. Let's see what it does. Invalid syntax. What is it? What's it complaining about? Oh. All right, X is not defined. So that we're doing 3, Y, pin 4. Well, let's get it to explain exactly what it's trying to do here. That may have been overbroad. I would have put something more specific. Right, so PIO for controlling the hardware pins, state machine defining the program flow, and then interacting with the physical pins, time delays, etc. Pin definitions, we're going to obviously need to use those in order to get reasonable input or output. The counter and the last state, etc. Then the quad function. So yeah, the function defines the logic for decoding the Quadrature encoder signals using the PIO assembly. So it reads channels A and B simultaneously using the in instruction. It initializes a counter X to track the encoder position. It enters a loop that continuously checks for state changes, and it waits for channel A to go low, checks the current state of B. Based on the change in B relative to its previous state, and the current state of A, it increments or decrements the counter, not the calendar, to reflect the motor rotation. Waits for changes to A to go high again before repeating the process. So state machine initialization is created using state machine constructor, and this allows for efficient execution of the PIO program defined in the Quadrature function. It takes several arguments, so it has 0, which is an ID for the state machine, which is not used in this example. The quad decoder, pin A, This passes the quad decoder function configured with the pin A argument to the state machine. Frequency is the clock frequency for the PIR program. And again, this doesn't have to actually match our physical clock frequency, so it's set to 10 megahertz. In base, the base pin for the input signal, so set to pin A here, as channel A serves as the reference for timing. Then all the rest of it we haven't reached yet. So, right, but if we run it, we still get the same error. So let's try searching and seeing through other sources if there's a way that we can actually get the reference for this. So let's say Pi Pico, Micropython. And let's do state machine. And we have the Raspberry Pi forums. Let's see what they got. Right, very similar here. They go and define the pins directly. We could double define it, but I think it might get angry. Right, so here instead of pin A, they do pin, and we would do 3. And this is really terrible. But we're just doing this as a troubleshooting step. It should pass by variable reference just fine. And let's get rid of this since it doesn't like it. Get rid of this reference since apparently it doesn't support it. Let's try running. Pin is not defined. Is that our problem? So let's do this. There are other ways to do this as well, which is we could use interrupts, things like that, and separate functions that are not state machines in order to be able to do this, but a state machine is the best way to do it, assuming it works. But let's look back at a machine library. Or at least our reference. Oh. Let's correct that syntax and test it first. Name machine isn't defined. Why isn't machine defined? It's a library. Wow, let's put this back. All right, so it does expect it to be by reference. It won't let us do it regularly. And I think that's kind of the crux of our issue. So let's do ASMPIO. We want to read the pins, so let's see what it's got. Let's see what Gemini has to say. All right, we could try that first. So what it's saying is that it wants us to just do in pins right here. 2. So it's saying read both A and B. Use pins instead of pin A. Wait, but if it's using that, why is it... Wait a minute. Why is it defining that? Okay. So here's what we got. So, both channel A and B use pins instead of pin A. Where is pins defined? Right, so let's Control Z this back to pretty much where it was before. Right, so we got this, let's run it. One positional argument. Let's just get rid of this and blank this out up here. Run it again. Pin A isn't defined, so we're exactly right where we were, but pins right here. Let's get some elaboration on this. So internal PIO registered, known as pins. Second argument defines the number of bits to read. Here 2 indicates that we want to read 2 bits simultaneously. So pin A variable represents the specific object. I'm actually not sure. We should check that. State machine, which is pretty much just doing what we want here. All right, so it shifts data in from source to ISR. So either pins X, Y, null, ISR, or OSR, and number of pins to shift. Doesn't really tell us a whole lot about our particular use case, more than we already got from Gemini. So worst comes to worst, we can actually just ask it, let's see if we can do it one of the other ways to do it a little bit dirtier, but I think it will, if it's not going to run for us because it is obviously not passing the appropriate signal or the appropriate variable names. Let's try it once more. So I'm going to do it on one of them and see if we can get the error to change to B. And it still says it's not defined. On line 23, which is our wait command right here. Let's see what it comes up with. So, I mean, it always starts with your right, which I always find kind of misleading because it could just be, you know, it doesn't always indicate that we've actually hit on something. Because it will always say you're right, or at least in my experience, it's always said I'm right, so I don't know what that means. Let's try it. Let's see what it comes up with. So it gave us a new option here. And some machine code here. I did say Micropython, right? Wait. Yeah, I did say Micropython. Yeah, it says it's Python. Just making sure. That would have been a thing. Okay. So let's get rid of this. It's not global. We're passing it here. All right. I just sidestepped the issue by defining it as a default. All right, so it says temp is not defined. Let's pass this back and find out what's going on with that. For the record, this is why programmers don't have to worry about their jobs being taken anytime soon. Just throwing this out there. So it says we can initialize it here if we want to. Well, let's see what we get. Yeah, I mean, this is like machine code. I don't know why it's saying... Either that or we don't have a library installed and it's not detecting that. Let's make sure we actually have stuff here. Let's try it. Again, it's not throwing any errors when we actually try and go into it. Nice, error. What did it say? Pretty much unable to install because I think it wasn't able to compile, if I had to guess. Can I expand this? So this is the actual console output, and a lot of times what you'll have with these packages and things like that is that they will actually try to compile it as part of the build. So, right, successfully installed pip setup tools, da-da-da-da-da. So it downloads everything in preparation for it, right? Build wheel. So it's trying to build wheel, which allows it to have root permissions, and it doesn't work because we're not on Linux. So I'm not sure why it does that. But we may need to actually install the full version in order for that to work. But we're not missing any packages. It doesn't say that we're missing any packages. And usually Python's pretty good about telling you if it can't import something. So it is able to get this particular portion of this package running. Let's see. So I'm just asking it for a more simplified example. And this is using interrupts, which far more simple and straightforward. It's not as sleek and probably not as efficient as the other one, but I have higher confidence in its ability to be able to function. Notice how it only has that one import, so the dependencies are a lot lower. So let's set this 3 and 4, save it out, and let's see if it runs. No, pin object has no attribute interrupt. Is it trying to do an ESP32? Let's see. Are we gonna have to log in to OpenAI and have it define this for us? It gave us completely different code. Okay, let's try that. Let's see what it's doing. So it's doing IRQs. Okay, we're getting better. It's saying that this parameter is not recognized, so it can't use that as the trigger. So I think that needs to revise that particular. But it's getting closer. It recognized the command that it was trying to use in there. Interesting. Why not? Let's try it. I'm just going to copy this all down here because it's where we're using it. I think it's just going to make it easier. Okay, it's doing things now. Woo! I don't know that it's printing anything out on the screen, but let's see what it does. I'm just going to turn it manually. Right, and we see there's a little LED light indicating that it has power. And this is working great. So, let's see, what is it actually doing? Where is it going to tell us anything? And it says it should be printing forever while true, just current count and then the counter. And it should be going up and down based on where it is. So based on current state and last state. I am not seeing it enter this loop, but I'm also not seeing it error out. So I have a feeling there may be an issue here. So let's reference our actual docs here, and let's do IRQ interrupt. So Pi Pico. So we got this, hardware interrupt detection, rising and falling. Right, and let's just take a look. I'm just going to do it as a comparison. And I'm curious if it just needs rising and falling instead of actually having to define those variables themselves based on what this example is saying. So pin dot IRQ rising and IRQ falling. And let's just comment out the second one. We only need one interrupt for the moment. It's not going to give us valid data, but it will at least tell us what it's doing. And it got unhappy. So let's try this again. And we don't have anything saved to the Pi Pico itself, so it's always going to boot up clean. All right, name time is not defined. Okay. So where is time defined? It's saying 37. So let's look at 37. So we need to do import time. So it did miss that. Perfect. So now I'm just going to do a thing, right? So we do see it doing a thing. So again, that was syntax errors related to how Gemini perceived things to be. Right? But notice how it's never really moving because the other state is not changing. Excellent. Okay. So now that we got that, let's actually fix the rest of our code by adding this back in. Let's copy pretty much all the trigger conditionals to be able to handle this appropriately, and then it should actually work. Okay. It's half working. Right, so I'm rotating this. It's going 1, 1, 1, 1, 1. Okay. So I'm just curious. Let's try running it. I'm just gonna set the output. I'm just going to set it to 3 volts. So it should spin kind of slow. And let's see what it does. And it doesn't do anything. So that's not enough voltage. Let's turn it up a little bit. Oh, I don't have the output on. Okay, it is spinning. Let's see, I'm gonna turn it up. So right now we're at 12 volts. Okay. So I'm going to try adding some resistance. So there's something to be desired in terms of our overall count. So I'm going to disconnect this and let's reverse it so it goes the other way and see if it goes negative just as much. And it doesn't look like it's reading at all in the other direction. Or is it? So how can we expand on this to make it more valid? Because this seems like garbage that it gave us. So we just spent an hour and we got nothing to show for it. All right, let's look at other options here. So let's see. Let's see what this wants. Well, I don't like that. That's going back the same road with the a significantly better solution, which is the state machine, but it is something where it's not doing what we want. But somebody else gave a different solution here. Looks like using arrays in ISR similarly to what we're doing here. All right, so let's try it. So we're going to copy the code. Let's try pasting it. Let's see what it does. It does nothing at all, which is fine. It didn't error. So let's take that. Let's see if we can find an example for this. Okay, so he actually did provide it. I skipped over it. So we're gonna test it. So we're gonna do 3 and 4, and then the while true. Well, let's see what it does. I don't know. Let's see. Encoder is not defined. It's defined here. We may need to put this at the bottom, which is fine. Time is not defined, that's fine. We need to import that. All right, so now it says it's not doing things, so let's see if we can make it do things. Right, so it's just showing zeros. Right? So that's good. So right now it's tracking the total number of pulses that it's seeing, and it's ever incrementing. Right, so I'm going to turn that off, and it stops, which is good. And now I'm going to reverse the direction. Okay. And we see it going forward. Sorry, didn't have this up. But you can see it kind of rotating. I don't have a piece of tape, although that probably would have been a good idea to kind of let you see what you're actually seeing with this. But it's a 10 RPM motor. It's very slow. But for what I plan to use it for, that's actually very fast. But we see the number changing. So I think there's an easy way that we can come up with a speed here. It's currently looping at once per second, right? So e.value, what we can do is we can track that value. And we can come up with change over time. So, for example, we will say, let's say delta. and we'll say last E. Right, so last E is E.value. Then we have delta is E minus last E. All right, and then we're going to print this value, and we're going to say and here's actually the big thing. We want to also come up with direction. So if delta, I'm not going to do the shorthand, but I will do this. So if delta is greater than 0, we'll do direction equals positive as a text value. Else if, so we'll do elif delta is less than 0, direction equals negative, and then we'll do an else statement, direction equals stopped. Right, that kind of covers everything. So what we'll do is, so we want to do speed, direction, and then the value. So we're going to do absolute value of delta. Direction. Right, and then we'll do in parentheses the value. And let's try running that. Perfect. Unsupported types for encoder and int. And I don't have this in the right place. No, I do. Oh, I may need to stop it and reset it. Let's do that. We just had it running. Let's try replugging it. $73. What's on 73 that it doesn't like? Oh, sorry. I need to pay attention to what it's saying. Okay. Right, so currently the direction is nothing, and it is stopped. Right, so we'll do the negative direction first. Oh, we didn't reset it. After it does the computation, it has to update the last E. All right, let's try that again. All right, we'll go in the positive direction this time. All right, so we see a pretty consistent time interval. It's running about 4,000. Right, I can barely stress it. Even if I hold on to it really hard, it still keeps doing its thing. Perfect. So I'm going to slow it down. So right now I'm at 6 volts. Okay. And we see a little weaker. It's running about half the speed. We're taking the interval every second, so realistically, we can say it's 2,000 RPM or so that it's running at right now. Before it was running around 3,600 or 4,000. It's a DC motor, so it's not synchronous to anything. So let's turn it down even more. Right? So right now it is at 3 volts. Okay. It's very, very difficult to stop it, but I can change the rotational speed quite a bit. All right. And now I'm going to stop it, and we should see it go to stopped. And notice how it is delayed behind the actual action, just for the record. So, okay. So we see it stopped in that direction, so let's reverse it, make sure it goes down. Right, it is actually rotating. I feel like I should get a piece of tape. I have a piece of tape. Let's put a piece of tape on. Look at it go. Wow. All right, so it is doing things. Okay. And we can stop it. We see it go to stopped. We can reverse it the other direction. So it's effectively doing what we want. It's a little more down and dirty than the PIO solution, which is something I've wanted to try for a little while, but I have no idea why it wouldn't cooperate. And to be honest with you, I don't have the experience with that particular command set enough to be able to troubleshoot it. You know, I do know that this is less efficient. You can't get quite the resolution that you would need to be able to do more higher speed motors. But for the purposes of this, I think it's just fine. Now, as far as the actual accuracy of this, I do believe I would need a tachometer or something like that to be able to calibrate this against, which I don't have, like especially an optical tachometer. But we can see as I put resistance here and slow it down, we do see that reflected in the speed. And something to keep in mind is because this is a heavily geared motor, even though this shaft on the input side is very low resolution, right? Because it only has the two sensors 90-degree offset to each other. So you're only getting the 4 counts, or the 4 pulses, well, technically 2 pulses per rotation. Excuse me. You're only getting the 2 pulses per rotation. It is still highly accurate because the output shaft is geared down, and that's directly attached to this in a way that can't slip, or you can't lose your relative position to it. So if you did have a way to be able to judge it, you know, to be able to come to an endpoint. So let's say you have a limit switch or something like that that you can calibrate off of, you can get consistent, repeatable positions based on that by counting the number of steps that you take to that point. So something I want to try and do with this, and this is something I don't know that it's going to be for this stream, just because we're already pretty far into it, but with the if you know your speed and everything else like that, you can actually create an adaptable an adaptable power supply for the motor in order to drive it, to be able to ramp up and down based on what the amount of power that you would actually need in order to drive a variable load. So it would be able to react to the load that it's under in order to achieve a speed. And that's what servos do, and that's a PID controller. I don't know that we're going to implement a full PID controller, but the idea is that I want to have pretty much a camera pan tilt controller using the controller that I built in previous videos. And what it is it's going to have one of these motors for pan, one of these motors for tilt. It will connect back to Raspberry Pi Picos, multiple, just to track each one individually. They'll be pretty much interchangeable with Arca Swiss attached to each side. So the motors themselves will be interchangeable, and then there'll be brackets pretty much in the middle that are Arca Swiss brackets to be able to connect them and attach the camera. So using that, you could do pan and tilt movements, create very consistent time lapses over a long period of time with very small and precise movements by being able to count the number of steps and be able to create that type of consistent performance. Because especially if I'm doing a very long, if I'm doing a very long panning move, it's going to be something where the wind could blow, any number of things could happen, but I would want it to be consistent so that way it looks incredibly stable. Same thing with doing tilt moves, things like that. If I, at some point, create the controller to be able to do a start position and a stop position, and I want to interpolate the position between those 2 points, I want it to be able to do it linearly across a period of time, so that way it looks very smooth and very stable, which is a lot better than, just going to one direction as fast as it can and going to the other direction as fast as it can. It looks like a very jerky movement, opposed to having that smooth kind of linearized, interpolated move. So that's kind of the deal. That's what the objective is. That's what the whole point of this is. I will post a link to the code just on a gist if you want to take a look at it. If anybody has any kind of suggestions or anything else like that, or wants to write a little snippet of code that we could try together, I think that would be awesome. And feel free to shoot it. Feel free to shoot it in, well, just reach out and we'll come up with a way that you can get me the actual code. You can email me at extendedgreg@gmail.com, actually. That's probably the best way to go. No attachments, it's got to be in the body, or it's got to be a link to a gist, which is the preferable option. So, but thanks for watching the video today. If you liked the video, be sure, or this live stream, now a video. If you like it, be sure to hit that like button and leave a comment down below. If you know anybody who would like this kind of content, be sure to share it with them. I would appreciate it, and I hope they would appreciate it too. And if you haven't subscribed, please subscribe. It helps me a lot with the YouTube algorithm, and also just gives me satisfaction knowing people are actually watching the content. So be sure to check out next time, whatever project it may be. So thanks for watching.